Welcome back to another new AMP podcast. AMP, of course, is the shorthand acronym for the Association for Materials Protection and Performance. I'm Ben Dubose, news editor with the AMP publications team, and I'm joined on today's sponsored episode by Greg Hansen and Brian Leinak from Sherwin-Williams Protective and Marine. In this show, we're going to look at a shift that's gaining real traction across structural steel markets, and that's the move from traditional three-coat systems to more modern two-coat systems. We're going to look at what's changed, where the time savings actually come from, how the performance is validated, and ultimately where this approach fits best. Greg and Brian, welcome to the podcast. Thanks for taking the time to join me today. Can each of you just give us a quick introduction and career bio? Greg, we can start with you.
Thank you, Ben. I've been with Sherwin-Williams since 1995. I'm currently the North American sales manager for the project development team. That is part of the Protective Marine Group of Sherwin-Williams. Our team works day to day with design firms, engineers, owners that have in-house design as well as design build construction companies to develop systems, answer problems, provide solutions to fight corrosion in steel and concrete business. I look forward to reviewing this topic. It's come up quite often in our day-to-day lives, and especially since construction projects are seeing new pressures of tighter schedules, labor constraints, and cost pressures. And we believe we have the technology to address those issues that now exist.
And Brian, same to you. Just introduce yourself to our audience.
Thanks, Ben. I've been with Sherwin-Williams since 2005. I'm currently the key account sales manager for steel fabrication. Areas that I cover are the United States and Canada. In this role and my previous role, I've been heavily involved in the bridge fabrication market and bridge and highway as a whole. And now I'm still staying with bridge fabrication, but also moving into the high value infrastructure market as well with our largest steel fabricators around the United States. And given the topic that we're talking about today is pretty much a daily conversation I have with somebody.
And for our listeners, we're going to keep this open-ended with Brian and Greg in that they can both jump in as they see fit. It's not that they each have to answer every question that I'm going to throw out. They can each speak to whatever is in their wheelhouse. So if you both want to address the topic, you certainly can. But if you want to defer to whoever's expertise it is, that's fine as well. We just want this to be free-flowing, a genuine conversation over the next 30 minutes or so. All right, let's talk about the basics. For listeners out there who are used to traditional three-coat specs, what exactly is a two-coat system and why is it getting so much attention right now?
Well, Ben, a traditional three-coat system typically includes a zinc primer for its corrosion protection, an intermediate epoxy to help provide that needed DFT build, and then a urethane top coat to provide weatherability as well as aesthetic appearance. The system works. It's got multiple decades of success on construction projects. But now we're seeing a time where all projects are fast-paced. They need, the owners do not have the extra time or the need for an extra coat or the extra expense to meet their needs. And so today we have the ability to provide a solution with the two-coat method. Now, in the two-coat method, you still have a zinc primer to provide that corrosion protection, but you have a high-performance finish coat that carries the responsibility of both the intermediate and the top coat that you typically see in a three-coat system. What are the major drivers? Well, as I said before, you have compressed construction schedules. In this day and age, with projects like data centers, for instance, we all have a need for our AI or our TikTok feeds. Those are very large projects that require a lot of power. So in parallel, we're building power generation into the market. And this puts a lot of pressure on construction and they need it faster. At the same time, because we have so much construction happening in parallel, we have shortages with labor and we have rising costs due to tariffs or due to overheads, price of fuel, price of insurance, things like that. So keep in mind, the owners of these projects still need corrosion protection and a stable aesthetic system, but they're looking for ways to save time and also save costs. So with the two-coat system, you basically are skipping a step, but we're not casually skipping a step. We're still using engineering to develop a coating that provides a layer that is backed by qualification data and real history. With both the two and the three-coat system, we can provide applications where 95% of the application can happen in a shop. And when you're in a controlled environment like a shop, the process provides you with a better application, better ability to inspect, better quality, and faster turnarounds when compared to field applications where quite often you're working off of lifts or elevated scaffolding.
I want to explore the time component a little more. In real world projects, what is it that actually slows steel down out in the shop? Where does the time actually go?
Yeah, the bottleneck usually isn't the application process, it's what's happening between the coats.
Hmm.
The real time thieves are curing windows, inspection holdups, touch up loops, and staging constraints. The reality in the shop is the steel may be coated, but that coating hasn't reached its cure to handle point and can't be moved out of the paint booth. Bays and racks are just staying occupied, and throughput suffers during those long cure cycles. The total potential wait time for a three-coat system can be 2 to 3 days before a piece of steel can be moved and loaded for delivery. That isn't labor time. You're not getting paid for that time. That's just shop time. The piece of steel is tying up space and slowing everything behind it.
So, with regards to the workflow, what is it that changes with two coats and what is it that stays the same?
Well, you eliminate the intermediate application step entirely. That's one less spray pass, one less cure cycle, one less inspection round, and one less touch-up opportunity. What doesn't change is the performance targets. Inspection discipline stays the same, film thickness, verifications, etc. Two coats demands discipline, probably more than a three-coat system, because there's no intermediate layer to hide a miss or a holiday. Removing one full application step can reduce coating labor in many shop workflows. The practical schedule point, the larger gain is often cycle time per piece, which multiplies across the entire steel package. Switching to a two-coat system with an organic zinc primer and a polysiloxane top coat can yield significant time savings. If a shop runs multiple shifts, a piece of steel could potentially be moved out during that same day. That's a fundamentally different throughput equation.
You mentioned organic zinc being a lot faster. Can you walk us through the difference between organic and inorganic zinc primers and ultimately why that primer selection is so important?
Yes, I'll handle that question. See, the primer selection is what sets the pace for the entire coatings application. It's the basis of the corrosion protection system right from the primer. Inorganic zincs, which are widely specified for corrosion protection, very common in government projects and bridge and highway specifications, actually would require a tighter surface prep control and longer cure times. Now, the cure time is based on humidity, and not just the relative humidity, but the actual ability for the air to carry what they call grains of moisture. So if I'm in a coastal environment that has warm, humid air versus a fabrication shop that may be in the northern parts of the country or in a high desert environment where I do not have that humidity, well, then my cure to recoat is greatly extended. Now, in the case of organic zincs, epoxy-based, that we'll talk about a lot today, they still provide the corrosion protection that we're looking for, but their cure behavior is faster and more predictable. And it's predictable because it's an engineered chemical reaction. It can enable recoating in fast as 30 minutes or 4 hours, not days. Inorganic zincs are typically based on their environment, and they would have to be verified by inspection before you even think of doing a recoating process. Because if they're not cured for recoat, then you're going to have to wait longer or create an artificial environment. All of this is time and money. And frankly, that's what we're trying to save.
Ben, it's important to note that AASHTO Product Evaluation and Audit Solutions, which is formerly NetPep to many out there that know it as that, their testing has shown no performance difference between organic and inorganic zincs in these two-coat systems. So there's no durability trade-off. You're not losing any corrosion prevention. And the time savings you'll get with organic primers is going to far outweigh the inorganic. Also, you're going to get the slip coefficient performance of a Class B rating for the primer, making it suitable for all applications. Organic zinc primers qualify under the AASHTO-related programs and are listed on the NEP code QPLs, or qualified product lists.
So one really good thing about Sherwin-Williams with the volume that you all work at and the scale, you've got a lot of real-world examples. So can either of you share an example of where these two-coat systems have actually been put into practice?
Yeah, absolutely. A great recent example is the Frederick Douglass Memorial Bridge in Washington, D.C. This is a new construction project that opened in 2021. All the structural steel was coated with a two-coat system with zinc-clad 4100 organic zinc primer and siloxane 800 polysiloxane top coat. The fabricator was Veritas Steel, and they were able to drop the intermediate coat going to this two-coat system, eliminating approximately a third of their labor costs. Going to eliminate several hours of waiting time just between each coat as well. By choosing the organic zinc over inorganic, the recoatability became predictable, as Greg was talking about, because organics are engineered by chemistry, making things easier for the fab shop, ensuring rapid deliveries to the job site. Best of all to the owner, they're still going to get that nice, clean, white, glossy finish and a corrosion prevention system that's going to last them 20 to 25 years.
So as you've mentioned a few times, this is a relatively new concept. So there's going to be a lot of asset owners and specifiers who want performance data. They want to see it validated. How do you get them comfortable with the idea that two coats isn't simply a shortcut?
Yeah, absolutely. You have to acknowledge that natural skepticism right there. Initially, owners will have that skepticism because they're eliminating a coat, which feels like they'll have less redundancy in their coating system. That concern is certainly understandable, but the comfort level comes from two things: the qualification data and performance benchmarks, plus tighter expectations around application quality as well as inspection. Case studies like the Frederick Douglass also help. In reference to evaluations, reduced coat systems pairing zinc-rich primers with a polysiloxane top coat met the long-standing corrosion protection performance that expected from a three-coat organic zinc system. This all works when teams control application quality, verify film build, and align an inspection plan to the project.
So we've talked a lot today about the primer and the mechanics there. I want to also spend some time looking at the top coat, because in the two-coat system, that's 50% of it. What does that finish coat need to do? And I believe you mentioned the polysiloxane earlier. Why do those come up so often as the choice for that finish coat or that top coat?
Thanks for the question, Ben. In a two-coat system, the finish coat provides durability, weathering resistance, meaningful film build, as well as aesthetics. These are all expectations that an owner expects from a provider. Polysiloxane technology is a hybrid, so it basically combines the properties that you would typically find with an epoxy intermediate and a polyurethane finish that would be used in a three-coat system. So you have the hardness of the epoxy, but you have the flexibility of the polyurethane all in one product. Now, Siloxane 800 from Sherwin-Williams is a good example of an isocyanate-free finish that's engineered for long-term corrosion control and weatherability. For work in the field, that isocyanate-free characteristics matters when schedules and multi-trade coordinations overlap. You see, you have less odors and less emissions from the coatings, means that you have less disruption and fewer access constraints during the applications. But in the context of performance, Siloxane 800 is compatible over both the inorganic or organic zinc-rich primers, providing both field and shop application flexibility. It's an excellent color and gloss retention while under the attack of both UV exposure or moisture or atmospheric pollutants. It's a hydrophobic technology. It has a very low surface tension, so it easily repels water. It resists contaminations from accumulating, and it's just basically easier to clean. Now, some of the other characteristics include direct impact resistance. So that helps with the rigors that we see from construction or transportation and erection when you have projects where the steel is coated in the shop and then shipped to the project. At the same time, because of its flexibility, its resistance to thermal cycling that the steel will see throughout the process, as well as its life cycle. So polysiloxanes become a clear favorite in this day and age of engineered top coats. Now, we do offer other hybrid technologies, such as polyaspartics. This is also a very valid top coat when it comes to two-coat systems, especially when you're looking for rapid cure times. But they're generally limited to use over organic zinc primers only. So therefore, polysiloxanes can provide that longer gloss and color retention, but then also have a broader primer compatibility.
You mentioned the bridge example earlier, but I know that bridges aren't the only asset that these two-coat systems can make sense for. So looking beyond bridges, where else in the world of structural steel do these systems potentially make sense?
Well, that's what I find funny about this business. You see, steel plate today that shows up at a fabricator doesn't know tomorrow that it's going to be a bridge or a water tank or a stadium or a data center, but the environment does know. See, corrosion is present constantly. So you need to be thoughtful when making a switch from traditional three-coat system to the two-coat system that may have as much case history behind it. And you shouldn't just go for it because the process sounds faster on paper. But the good news is that switching to the two-coat system is defensible because we have validated it, not just in the lab, but in real life projects, all types of projects. So at first, let's talk about stadiums. You know, the owners are creating a high visibility. They're creating high contact. Hundreds of thousands of people will walk through these facilities bumping this steel. Durability against scuffs, abrasion, and incidental damage are critical. These are very high traffic areas. But at the same time, aesthetics matter to the owners. You know, quite often it could be just for the architectural intent, or it could be the fan experience that the owner intends to make the standard of their stadium. And many times it's part of the marketing of the stadium or the team. Now, the low surface tension of the technology helps provide resistance against graffiti or dirt pickup, which makes maintenance and cleaning between events very easy. Now, some of the stadiums that we can mention, SoFi Stadium in Los Angeles comes to mind. In this case, it was a global project. The steel, 90% of the steel was actually fabricated in China, loaded on a barge and shipped and delivered in Los Angeles, where it was erected, then touched up and put into service. Other stadiums that are currently in the process include the Tennessee Titans Stadium, the Buffalo Bills new stadium, as well as New York Football Club's stadium that's currently being built are using the same epoxy zinc and polysiloxane top coat. Now, other bridge projects that come to mind, the International Gateway Bridge in Long Beach, as well as the Big Sur Bridge in Monterey County in California, are two other examples. The owner was looking for technologies that easily could shed the hydrocarbon deposits from the chemical and train exhaust that can stick to the bridge. Now, due to the low surface tension that I mentioned about polysiloxanes, many of these contaminants could actually be washed away or shed just from sufficient rainfall, or light pressure washing can easily clean them up very quickly. We also see the use in advanced manufacturing, data centers, as I've spoken to earlier, semiconductor labs, and EV plants. The finish is very stable. It has a predictable timeline. And some of these places are also very sensitive to coatings that have outgassing issues. Siloxane 800 completes the outgassing testing with only a few days of cure, allowing it to be the perfect construction efficiency top coat. And then when you start talking about manufacturing facilities like food and beverage or pharmaceutical, these are facilities that see frequent washdowns or persistent wash conditions. And sometimes they're even washed with elevated temperatured water, or they have long dwell times with their cleaning products. This technology is very chemical resistant. And again, that flexibility allows for that thermal shock. And then there's also projects that we do in the water wastewater structure. Elevated water tanks, for instance, can see condensation when you have warm, humid air coming in contact with steel that on the other side has nice, cool water. This condensation allows for dirt to attract to it, and that dirt then becomes a feeding source for mold and mildew, especially if you're in climates or in parts of the country that have high vegetation. The beauty of this hydrophobic technology with a low surface tension is that it easily sheds this contaminations and extends the life cycle of the coating system. Algae control is also an important aspect when it comes to water wastewater service. So the low surface tension that I mentioned helps shed the environmental contamination and makes surfaces easier to clean with power washing. So there's less aggressive effort, less time used by the maintenance crew, which leads to less cost. This equals greater sustainability, which is important to all owners.
So even with all of those advantages, I'm sure there are still some skeptics. What pushback do you guys hear from the market, and how do you all respond to those?
Well, Ben, the initial objection is the price per gallon typically of the polysiloxane. Yes, it is more than your standard polyurethane, but labor is one of the highest costs in the whole process, and you're eliminating a full application step. That labor savings alone far outweighs any material premium. And if you sit down with an asset owner or an engineer and explain to them the price per square foot of going to a 2-coat system versus what the 3-coat would be, it becomes very obvious that paying a little bit more for a gallon of paint with a polysiloxane, it just doesn't matter in this situation. Then there's also we talked about it a little bit earlier, the 3-coats feel safer. We agree that the discipline matters with 2-coat applications, even more than 3-coats. However, with trained applicators and a rigorous inspection plan, the performance of the 2-coat system will live up to the testing and the verified case histories that are out there. Masking and connection detailing always comes into play in a fabrication shop because that takes a lot of man hours as well. Masking and detailing will always be there. We understand that, but again, the elimination of a step saves time and labor during the masking process. And then edges, angles, and the complex geometry that go into a lot of these structures. High solids, high volume coatings improve edge retention of the coating. Good paint practice still applies. Stripe coating on edges, welds, and bolts is always best, and we're always going to recommend that no matter what coating you use.
We've talked a lot today about shop application, but there's a field component to consider as well. So what about some of those hurdles that folks can encounter in field jobs in terms of transportation, erection, touch-ups? Just speak to any application challenges that are potentially out there from a field perspective.
Yeah, even the best shop applications face field realities. Connections will get damaged, surfaces pick up dirt on transportation, bolted areas need protection. Systems with practical recoat windows and predictable field cure help crews protect damaged areas and keep the progress moving. Polysiloxanes have a practical recoat window over themselves, so field touch-ups go directly over that existing finish without compatibility concerns and excessive preparation. Primers for fieldwork are typically organic. Inorganic zinc primers are optimized for the shop, but that field, you need something that can tolerate a wider range of environmental conditions. That's where the organic zincs come into play and work really well in field application. Polysiloxane technologies are isocyanate-free, which can improve health and safety review processes. Plus, there are no fumes chasing out other trades off the site. These technologies support multi-trade coordination. Other crews can keep working nearby, which is critical when construction schedules demand multiple trades in the same space at the same time. This will minimize any scheduling impacts on coordinated trades.
Let's talk about the long term and what the total life cycle picture looks like with these 2-coat systems. Are asset owners giving anything up over the life of the asset that they're protecting here?
Well, we would completely agree. The idea was to generate a technology that has the same service life expectations. So if we're looking at 25 years of corrosion protection, but then we're providing a faster throughput solution. You see, the technology is straightforward. If water cannot get to the steel, it won't corrode. Now, when it comes to maintenance, the less corrosion that is underneath, then the less work and the cost during that maintenance cycle that an owner must incur. Now, at the same time, as Brian had mentioned, the technology does have the ability to recoat over itself. And there now, if we have a nice corrosion protection in place, we're looking at an additional 20 to 25 years of service versus full removal and rebuilding the entire system. Now, the system is recognized in the industry. AMP, for instance, has created a performance standard specifically for polysiloxane technology. So the industry continues to lean into this chemistry. You see, we're looking for systems that can provide less waste, fewer emissions, and reduce disruption, which provides expected service life cycles and sustainability. Traditional 3-coat systems have a similar service life. The advantage of the 2 coats is that all of these efficiencies, which include shop or field applications, the cost reductions along the way, the same protection, fewer steps, faster delivery, lower total cost of ownership are key takeaways of the 2-coat systems.
All right, so as we wind down this sponsored episode, I want to get to the bottom line. If someone out there listening is evaluating these 2-coat systems for an upcoming project of theirs, what's the decision framework? What are the practical steps that they should consider in their evaluation process as they're trying to make a decision about whether a 2-coat system is right for their project?
Well, Ben, that's a great question. I'd say the owner needs to start by evaluating the performance target and exposure environment, not just the number of coats. Treat this as a system decision, primer plus top coat plus process. Ensure you are meeting specific approvals, testing expectations, and specification language. One thing we know is a 2-coat system will remove a costly step without changing the performance target when specified and executed correctly.
You know, I'd have to add, Ben, that one should think about the constructability. How does the coating system affect the overall construction schedule, not just the coating schedule? You're looking at fewer steps, faster cure, less labor coordination. It adds up across the entire project. Put the pieces together, primer, top coat, and process, as Brian had said, and you get fewer steps, faster release, and a finish that holds up over the long haul. The data supports it, the field history supports it. And I'd like to add as a final note, if you have any questions and want to explore the benefits of 2-coat systems I have to offer, then be sure to reach out to your Sherwin-Williams Protective and Marine Design, Engineering, and Pre-Construction Services team to talk through your specific project.
Excellent insight there from Greg Hansen and Brian Lyanak. Gentlemen, thank you so much for joining me today.
Thanks, Ben.
Thank you, Ben.
All right, with that, we can put a bow on today's episode. Really great perspective there for anyone that's potentially looking at making a decision on what coating system to use for a structural steel asset. And for any listeners that might want to dig a bit deeper into this topic, just visit protective.sherwin.com or email swprotective@sherwin.com. And as far as our team at AMP, if you want more from us, the simplest way to get more from the association is by visiting amp.org, ampp.org, and you can find all sorts of resources. Greg and Brian mentioned the standards, which we've got tons of info on those, but also our publications within the association. Just check out the tabs on the amp.org homepage, and you can find more from me and anyone and anything within the association. All right, with that, the plugs are complete, and I think we're done. Thanks to all of you for listening, and we'll catch you again next time.